Hey everyone, welcome to today's Explainer. If you've ever stared at a tangled mess of wires or maybe looked at your monthly electric bill and thought, what on earth is actually happening behind these walls? Well, you are in the perfect place. Today, we're completely mastering the fundamentals of Class 10 electricity. And don't worry about getting bogged down in complex abstract physics, because we're going to demystify the whole shebang using a super intuitive analogy: water flowing through pipes. Trust me, by the end of this, those scary textbook formulas are actually going to make perfect real-world sense.
Okay, here's our quick roadmap for today. First, the flow and the push. Second, Ohm's law and resistance. Third, wiring, looking at series versus parallel. Fourth, the heating effect. And finally, power and energy bills. Let's get into it. Section 1, the flow and the push. Moving electric charges.
So what exactly is electricity? It sounds like a massive philosophical question, right? But it's actually explained beautifully in our sources. Basically, think of electricity exactly like water flowing through a pipe. Instead of water molecules, you've got these tiny electric charges moving through a wire. The faster these charges move, the higher the current. It really is that simple. But, okay, there is a funny little historical quirk here. Even though tiny, negatively charged electrons are what's actually physically moving in one direction, by convention, we always draw the electric current moving in the exact opposite direction. Literally, the direction positive charges would flow. Just a weird quirk to remember. So let's put a formal definition to that water flow. Electric current, represented by the letter I, is simply the rate of flow of that electric charge. The formula is super straightforward. I equals Q divided by T. That's charge, which is Q, divided by time, which is T. We measure this flow in a unit called amperes, or amps for short. So going right back to our analogy, saying a circuit has 5 amps is literally just like saying a water pipe flows at 5 liters per minute. But think about it. Water doesn't just flow on its own, does it? It needs a pump. Well, in an electrical circuit, the charges need a push too. And that push is called potential difference, or voltage. This comes from a battery or a cell. Without this crucial push, the charges just sit there doing nothing, and your light bulb stays totally dark. Mathematically, it's V equals W over Q, which is just the work done to move a unit charge from one point to another. And we measure this vital push in volts. Now, to measure these two vital forces, we use two specific tools. And hey, pay attention here because this is absolutely a top topic for exams. On one side, we have the ammeter. This measures the flow, the current. Because it's measuring what's actively going through the wire, it has to be connected directly in the path of the electricity, what we call a series connection. On the other side is the voltmeter. This measures the push, or the potential difference between two specific points. So you place it alongside the component, measuring across it, in what's called a parallel connection. Section 2, Ohm's law and resistance. Let's talk about electrical friction. All right. This brings us to literally the most famous rule in electricity, Ohm's law. It states that V equals I times R. Or, to put it into our everyday terms, the push, V, equals the flow, I, multiplied by the friction, R. This means if you provide a bigger push from your battery, you're going to get more current flowing through the wire. Well, provided the temperature and the wire's resistance stay exactly the same, of course. The relationship is directly proportional. It's a beautifully simple concept. But you might be wondering, what exactly makes up this electrical friction, this resistance? Well, there are 4 main factors. Number 1 is length. A longer wire just makes it harder for electricity to get all the way through. Number 2 is area, or thickness. Think of a thick wire like a wide, multi-lane highway. It's way easier for the current to travel through that than some narrow little dirt path. Number 3 is material. Some materials, like copper and silver, naturally have very low resistivity, which makes them fantastic conductors. And finally, number 4, temperature. In most metals, when the wire gets hot, the atoms inside start vibrating more, making it much harder for those electrons to squeeze past. Section 3, wiring, series versus parallel. Let's see what happens when we start joining multiple devices together. So when wiring things up, we basically have 2 choices, series or parallel. In a series circuit, everything is in one single line. The total resistance just adds straight up. Rs equals R1 plus R2 plus R3. And the exact same current flows through every single bulb. But here's the massive catch. If just one bulb breaks, the whole circuit is broken and everything goes dark. No good. In a parallel circuit, devices are set up side by side. Here, the total resistance actually drops, calculated as 1 over Rp equals 1 over R1 plus 1 over R2 plus 1 over R3. Each device gets the exact same full voltage push from the battery. The brilliant advantage? Independence. If one light goes out, the others stay on. And yep, this is exactly why the circuits all across your home are wired in parallel.
Section 4. The heating effect.
Okay, so the crucial point here is what happens when electricity really struggles to get through that friction we talked about earlier. Have you ever touched the wire of a high-powered appliance and noticed it felt warm? Well, when electricity pushes through high resistance, that energy has to go somewhere. The electrical energy gets dissipated as thermal energy. The wire literally heats up. Now, sometimes this is a huge problem, but actually, a lot of the time, we engineer our devices to take full advantage of this.
And that brings us right to Joule's law of heating, which tells the whole story. H equals I squared times R times T. Basically, the heat produced depends on three things: the resistance of the wire, how long you leave it turned on, and this is the most important part, the square of the current. Since the current is squared, if you double the current flowing through a wire, you don't just double the heat. No way. You get 4 times as much heat. It's an exponential jump.
We actually use this heating effect every single day. Step 1, think of electric irons or space heaters. They use special alloys with high resistance, so they intentionally get red hot. Step 2, traditional incandescent light bulbs. They use a super thin wire made of tungsten. It has such insane friction that it gets white hot. We're talking upwards of 2,500 degrees Celsius here, and it actually emits light without melting. And step 3, the humble fuse. This is a genuinely brilliant safety device. It's a wire with a purposely low melting point. If a dangerous amount of current tries to flow into your house, the fuse gets hot, melts, and snaps the circuit, literally saving your home from a fire.
Section 5. Power and energy bills.
So we've talked about the physics, the flow, the heat. But how does all of this translate to the actual electric bill you pay at the end of the month? Well, it's all about power. Electric power is simply the rate at which an appliance consumes electrical energy, and we measure this in watts. The primary formula is P equals V times I. Power equals the push multiplied by the flow. Now, thanks to Ohm's law, we can also write this as P equals I squared R or P equals V squared over R. You just use whichever formula fits the numbers you're given in a problem. Simply put, a 100-watt bulb is just consuming energy faster than a 10-watt bulb. But here's the thing. When the electric company sends you a bill, they don't count every single joule of energy. That number would be ridiculously massive. Instead, they use a commercial unit called the kilowatt hour. So what does that actually mean? Well, 1 kilowatt hour, which is just 1 unit on your bill, is exactly the amount of energy you'd use if you ran a 1,000-watt appliance for 1 full hour. To put that into perspective, 1 single kilowatt hour is equal to a staggering 3.6 million joules of energy. Pretty wild, right? All right, I want to leave you with this final practical thought experiment straight from the sources to prove you've mastered this. Which uses more actual energy, sitting and watching a 250-watt TV for a full hour, or firing up a massive 1,200-watt toaster, but only for 10 minutes? Let's do the math real quick together. Energy is power times time. The TV is 250 watts times 1 hour, which equals 250 watt-hours. The toaster is a whopping 1,200 watts, but 10 minutes is only 1/6 of an hour. So 1,200 times 1/6 is 200 watt-hours. Surprisingly, the TV uses more total energy. So I leave you with this thought. Knowing that heating elements drain power so quickly, how much is your daily 15-minute hot shower actually costing you compared to binge watching your favorite TV show all weekend? Go check your electric meter, do the math, and keep questioning how your world works.